Good morning. Can everybody hear me? Terrific. My name's Jason Kinchin. I'm the Vice President of Engineering for Paradigm4, and I can't tell you how happy I am to be following the previous gentleman, because I think we've got a real interesting opportunity to solve some of the challenges that he was facing, the problems he was facing in terms of some of the limitations that maybe he was running up against in terms of these huge data sets and data mining opportunities. But before I get to that, let me just tell you a little bit about our company and what we do. We are a Mike Stonebreaker company, and I don't know, does anybody know who Stonebreaker is? Yeah, so he's in the CS world, he's very famous, and he is kind of the godfather of databases and data stores. So you might recognize some of his companies, Ingress, Postgres, other companies that he sort of launched that have become, kind of lingua franca for databases in the world. But one of the things, he's at MIT, and there being no shortage of scientists at MIT, they were starting to have big data problems as well. And so what was happening was, and he basically put this philosophy together and engaged in this conversation with scientists all over the world, and came up with this idea that, well, of course, sort of traditional data stores have tabular format, named fields, rows and columns, and that's great for business. That's great for transaction databases. It's really horrible for scientific data, as probably, I see a couple people nodding out there. So what our company was founded on was this notion that a data store can have as its elemental object not a two-dimensional table, but a multi-dimensional array. Okay, so that's what we built, a data engine whose primary data structure is a multi-dimensional array, not a table. Okay, so just sort of looking at some examples of how data is stored. Basically, here's some mass spec data. We have it's in dimensions, no limit on the amount of dimensions, single data model for sparse and dense matrices, and we can have many attributes associated with each cell of data. So here you see some mass spec data. You see doubles, you see a Boolean. You can obviously have integers. You can have strings. You can have user-defined data types, and they can all be associated with the cells. Now you can see these are the pixels in the mass spec data, and you see not only that, but the M over Z calculations. But you can also imagine that coming out of the screen are slices of spectrograms that might be slices of tissue, and you might see another dimension that is subjects, or you might see another dimension that is instruments or processes or whatever, or all of the above, right? And the whole notion here is that you can slice and dice through any of those dimensions and get your information out. Okay. Here's sort of a comparison. This is a kind of a wearables example, a graphical representation of a wearables example. But it sort of tells you immediately, what kind of challenges you're going to be facing if you're using a table model. Whereas if you're using a multidimensional array, again, you've got all the data co-located, and then we've architected it so not only is the data co-located logically, but it's co-located physically as well. So that for performance reasons, you can get at all the attributes of a disk, and we sort of anticipate the dimensionality of it and how you're going to slice it. And so you get very good performance, and it's available for all kinds of hand optimizations, or we can take a crack at optimizing it ourselves. But basically, multi-dimensional blocks of data are the Franca. So this sort of talks about, so since it's an enterprise product, you can have many couplings with the data, right? So you can have a language coupling. We're very sort of tight coupling with R, with Python. Would be easy to do with MATLAB or any other sort of analytics package. I was at MathWorks for 20 years, and we were running into this problem when I was there. So these huge telemetry runs were being done, and you just couldn't fit them into data. So I'm really excited to come to Paradigm4 and talk about how you can do these analytics, these principal component analyses, these statistics, these signal processing algorithms across data that does not and never will fit in memory. So you can imagine these analytic tools. You can build RESTful APIs for web apps, and then down at the other end, sort of figuring out what algorithms you want to apply to the data using these tools. So we've been using Caffe. We just last week had our first TensorFlow machine learning demo, and that was a very big success and a kind of a milestone for us. So, but the point is that as an enterprise tool, the couplings are where you want them to be. This also demonstrates we can, as a multidimensional array, you can iterate over the cells using your own proprietary algorithms written in R, Python, and MATLAB. So this is sort of, if you're going to address, say, a Monte Carlo simulation or some kind of MapReduce problem, there's an easy way to apply an algorithm across the thing, and that's a technology we've named streaming. But a lot of products and projects have that, and we have it as well. So this is sort of this is sort of a generic slide that I use, but it kind of talks about the cold data, the warm data, and the hot data, right? And so basically, unlike sort of a traditional databases where the data is just there, you can actually pull the data out and save resources for when you need them. So this would be like stuff that's archived somewhere, it's on tape, or it's in a cold storage thing. This is stuff that's available to be queried, and then this is stuff that you're actually actively working on doing analysis on. It's being pulled into the analytics. The reason why this slide is important is that we have our proprietary CIDB format, but there's no reason why this couldn't be an HDF5 or an ADF format, and I'll talk about that in a minute or two. Okay, so basically I decided we have this great technology for doing large-scale analytics, and Allotrope has this emerging standard for data and data formatting, and how do we bridge those two worlds? And so I took two basic approaches. One is that I wrote a loader. I wrote a loader that brings data into our data engine and writes it back out. It maintains total integrity, total structure. All the information in the ADF file is available in the database. The other one is a project that was done in the last year by some friends of ours at our house. We work with a lot of academics who are open source, and they wanted to do this prototype called Array Bridge, where the data itself is actually maintained and stored in HDF5, but you can run the query languages and do the analytics there, but there is no materialization of the data into the database. So it's like its own data store. So it's like they took out the storage engine that's native to our data engine and put HDF5 underneath it. So we have and they build wrappers around them so that the language can deal with them in situ. Okay, so I'll talk a little bit about both of these techniques. So the loader, basically I was looking around for large ADF files, and it wasn't until I got here that I realized that there isn't that much ADF data out there. I kind of wish I'd had the previous gentleman's data, because I would have loved to deal with a terabyte of data. That would have been fun. Sorry? Tomorrow, excellent. So basically I went into the wiki page. I found some largish files. I wrote a loader. This is on a very modest system. I did this. We're pushing a release out. I shouldn't even be here. I'm trying to. My guys are back pushing a release out. So kind of in my spare time, while I was running tests and waiting for results and in between meetings, I just wrote this thing on my own desktop server, which you can see the specs for it there. Single node, 4-instance configuration, and very naive implementation. I didn't do any tricks in terms of piping or FIFOs or anything like that. This is just native load times. And so to get one of these largish files off the file system and into CIDB was never longer than a minute. Okay, I'm sure the previous gentleman's it would have been a little bit longer than that, but probably not as long as 40 hours or however long he suggested it. And again, there are lots of ways we could tweak that and optimize that so that the load times could be significantly reduced. And then I was able to, having these 32 files loaded into memory, I was able to do computations across the data sets, right? So I was able to find all the peak identifications in all of the runs. I was able to do variance on them. I was able to take their standard deviation. I don't know if that's anything anybody wants to do, but I was able to do it. And the computations result on my modest machine returned in, sometimes they were very fast, but, even the most complicated ones came back in 20 seconds, okay, on a very modest machine, okay? Now let's talk about the array bridge stuff. We didn't do array bridge at SciDB, like I say, it was done at Ohio State. But here's the basic idea of it, is that our data store is basically replaced with the HDF5 files. So you create an array, give it the specification of the HDF file, and it reads, it loads and writes the data directly to the HDF5 file. So there's lots of reasons why you might not want to take all the ADF file and put it into a database in a completely different format, right? You want a single source of truth, like that. So this is kind of the idea behind that, is that you can query any of these files as if they were SciDB arrays for any of the amount of data that you might want to use, and do the analytics based on that. Now, interestingly, like the previous gentleman, if these files are huge, you're sort of giving up, the disadvantage is that you're sort of giving up the advantages of a distributed data store, right? So when we bring our data in, we're distributing it across nodes, we're building caches, we're doing replication, we're doing all kinds of nice stuff to make things performant and safe. But here's just sort of like bringing data into a query. These were things, and they were very, very nice comparable numbers, just to get the data out of the files and into the system. So those are the comparisons, and really the message here is that they're all about the same. That the work that they did, it didn't matter if it was an HDF5 file, the data could be retrieved as quickly as if it was native SciDB or if it was a standalone C program. Okay. Now, once you do what you do with it after that is sort of a different story, and that goes to the distributed data store. But just getting it off the machine was pretty impressive. So this is kind of what I want to sort of leave you with, is that we are starting to imagine, as the previous gentleman was, use cases that involve breadth and depth of data like we haven't seen before, right? So we're imagining use cases of data mining that involve hundreds, thousands, tens of thousands of ADF files simultaneously, right? And then instrument runs that might produce a terabyte of data on a single run. I was talking to somebody about that yesterday, okay? So you've got depth and you've got breadth, right? And you're gonna need a tool that's designed for that style of data mining. And those were only two variants on an idea of round tripping from an ADF file into the data engine. There could be many different approaches and many different hybrids of those two, for example. But basically, once the data starts to grow, you're going to start to want, a lot of the things that you get in traditional enterprise data engines, right? So you're going to want to have multi-user. You want to have transactionally safe access to these files. If you're reading them and updating them, and multiple users are using them, you want to make sure that they don't stomp on each other and that the data integrity is maintained. You're going to want to scale, right? As these things get big, you want to say, wow, this is too slow, or this is undoable. Let me add another 4 servers. Let me add another 16 instances, and all of a sudden your data is performant and retrievable. You want central administration. The HDF5 files have lots of advantages in terms of their, say their chunking and the way their data is organized. All of that stuff could be administered centrally with a central database. And then obviously a lot of what as these things go into mission critical and enterprise critical areas, you want high availability and fault tolerance. As many users as you're going to have dealing on this, and if you have failures of your systems, you don't want your data to be corrupted. Okay. So when I was listening to the previous gentleman, I was getting all excited. I feel like we have a conversation to be had. But I was also thinking of this gentleman and the questions he was talking about in terms of in terms of he had that were developing the ontology. And I think, well, what about the questions? You know, what is the sample? What is the group? What is the and then, so aren't you going to want to ask, you know, what are all the injections associated with a sample? What are all of the peak values associated with those injections? What's the variance of them? Do you want to query based on a threshold of peaks? Do you want to do statistics on this stuff? And that's where, you know, I think a tool like our data engine would come in. So I don't know how fast I went. Maybe time for a couple questions people have.